Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Alhamdulillah, in this morning we can continue our meeting. And in the past meeting, we already finished our discussion about bit mask and bitwise operation. So today, inshallah, we want to continue to the next topic, which is Fenwick tree. All right. So before we start our discussion, let's begin with praying together. Allahumma inna nas'aluka ilman nafi'an wa rizqan thayyiban wa amalan mutaqabbala. Allahumma inna na'udzubika min ilmin la yanfa' wa min qalbin la yakhsha' wa min nafsin la tashba' wa min da'watin la yustajabu laha. Rabbana zidna ilma warzuqna fahma. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Amin. All right. So let me share the screen. And I have give you some problems about Fenwick trees, and maybe some of you already solved many of them. So maybe for some problems that you already solved, we can discuss them quickly. So we can discuss the others that you haven't solved yet. All right, but before we start the discussion about the problem one by one, let's discuss what is Fenwick tree. And maybe some Fenwick tree problems can solve by segment trees. Okay, yes, maybe some of you can solve the problem using segment trees like this, because the characteristic is quite similar. So both of them can solve range query. So what Fenwick tree can do? So Fenwick tree can do point update, and also prefix query. But if we can do inclusion and exclusion to a specific operation, such as sum or product or XOR, then we can do range query using inclusion and exclusion. All right, and both of them can be done using segment tree. Okay, so segment tree can do point update, even segment tree can do range update, right? And also segment tree can do prefix query, even can do range query without inclusion and exclusion. So even if the operation is minimum, maximum, or greatest common divisor, or and so on, we can do range update or range query. That's why segment tree is more powerful, so we can solve some Fenwick tree problems using segment tree. But what is the advantage for Fenwick tree? Of course, the implementation of Fenwick tree is simple. So segment tree is more complicated. All right, that's why when the problem can solve by Fenwick tree, then it is better to implement Fenwick tree instead of segment tree. And the complexity is actually same, but Fenwick tree is faster. It's little bit faster from the constant. All right, so the complexity to do point update is just same, which is n log n, and the complexity to find the query is also n log n, but Fenwick tree is faster. And the memory is just same, which is on. Segment tree is also on, but around 04n. Okay, the complexity is same, but the constant is better in Fenwick tree. All right, and maybe some of you already know how to do point update and prefix query in Fenwick tree. How to do that? So at first, let me show you the implementation how to do point update and prefix query. So yeah, maybe you already solved them, already know how to implement them. So maybe some of you can try to implement your your own style. You can also copy paste from the problem that you already solved it before. Okay. Maybe let me erase this first. All right. Yes, you can find this significant bit using this. What is least significant bit? Least significant bit means the biggest to the power of k. For example, let me create another definition of least significant bit. Least significant bit is 2 to the power of k, where k is the maximum integer satisfy or satisfies 2 to the power of k divided x. All right. Or maybe we can write it like this: x modulo 2 to the power of k is equal to 0. All right. This is least significant bit. Or if we write it in binary representation. If we use binary representation, then find the rightmost. Yes, yes, list one bit. All right. First means the most right or the rightmost. Yes, LSP is least significant bit. All right, and in order to update, we can use like this, or we can make it less than or equal when we need to query until n. Okay, yes, we will use I here, yes, or less than max n. All right, and then what is the definition of ft? Ft is the sum of, or let's make it a I minus the significant bit until a I, like this. So Fenwick tree is the middle between original array and prefix sum. In original array index I only consists of value in index I. But in prefix sum, pref I consisting of all of the value from A1 until AI. But in Fenwick tree, we are not only storing itself, but not storing all of the value, but just storing 2 to the power of k. Or let's define it as pref I minus pref I minus the least significant bit of I. Okay, what does it mean? So if we are storing index 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, then 1 only covering itself and 3 also covering itself. All odd numbers only covering itself. But for even number, it covers more than 1 numbers. So if it is divided by 4, then it will cover 4 like this. If divided by 8, so it will cover until 8. And also if it is divided by 16, then it covering 16. All right. So if we want to do update, when we use prefix sum, it means we will update all of the value from I until n. Is it correct? So when value of AI is changing, then the prefix sum from I until n will be changing. But how about in Fenwick tree? In Fenwick tree, for example, when the value of 5 is changing, then the value changing is only ft5, ft6, ft8, ft16. So not much. The number of changing value is just O log n. So the complexity is just O log n, not On. Alright. That's why we can update using this. So starting from I, then just add least significant bit, become 6, then add least significant bit, become 8, and then become 16, and so on. So it means we already increase all of the value that covering index 5. And the other index such as 1, 2, 3, 4, 7, 9, 10, they will not changing since they are not covering index 5. Okay. And how about when we want to find the perfect sum? So if we use perfect sum, then just use pref I directly. But in Fenwick tree, we cannot directly use FTL. But after we use FTL, try to add with L minus least significant bit. For example, if we want to find the sum from index 1 until 13, it means we have to add to sum up from 13 and then 12 and then 8. That's why after adding FTL, then reduce L by least significant bit. Alright. And it's quite magic. Maybe at the first time we don't get the intuition, but just implement it like this. We can also use for like this. Alright. Yes, we can use less than max n or less than or equal to n. Okay. And for query until I is equal to 0. So while I greater than 0, just add the answer. And also the significant bit can also represent that with this formula, and no need to use bracket. You can also remove the bracket. So the formula is like this. Alright. So is there any question for this problem? And actually, there is another function other than update and get. We also can find the first prefix. So we can find the, for example, minimum x, so that pref x is greater than or equal to y. Alright. Can we find the minimum index so that the prefix is greater than or equal to some constant? Alright. Just like in segment tree. In segment tree, we can also do that. Maybe you already know about it. So in segment tree, we can do binary search in just O log n. not log square n. If we use binary search and then combine it with query in segment 3, then okay, the complexity will be log square n. But we can optimize it, so the complexity is just O log n. How to do that? In order to do that, just check what is the sum of the left. If the sum is still less than y, or yes, less than y, it means you will go to the right. Then just check, just add with this. Is the sum greater than or equal to y? If greater than y, so don't use it. So we will do binary search here. If we try to add this, if still less than y, okay, then we will try to do binary search here and so on. So we can do binary search inside segment 3. So the complexity is just O log n, not log square. And how about in Fenwick tree? We can also do this in O log n. So no need to do binary search combined with query or prefix query. But we can directly use the property of Fenwick tree. So we can do binary search inside Fenwick tree in just O log n. Yes, you can do this. And some people call it binary listing, not binary search. Okay, some of you already know the implementation. Maybe let me implement my own style. But this update function, and then this is prefix query function. Yes, thank you. All right, this is the implementation to find the prefix sum. And then how to do binary search or lower bound in Fenwick tree. So we can use this. We can use logs constant. For example, log is 20. Yes, here. So I usually implement it like this. Right, this is my implementation. Okay, then let's check. I think the meter parameter of 4 cannot empty. It is should be like this, or you can also write it like this, but cannot empty. This is should be the condition when we still continue the looping. The first one it can be empty, the third one can be empty, but the second one cannot empty. All right, yes, this is. But I afraid when we only declare until a specific size. I think if you use this, then you have to make sure that you define the Fenwick array 2 to the power of 21. All right. But in my implementation, we can declare it just equal to the constraint. If the constraint is just 100,000, for example, just make it like this. Okay, yes, maybe you can write it in one liner. Okay. Yes, because in order to avoid out of bound in the array. But in my implementation, I already checked is the id is less than or equal to n. If greater than n, it means not valid. So just undo the jump. After we jump to the power of I, and this is invalid, so just go back to the power of I. All right. And also if we jump and the sum is greater than or equal to x, then just go back. But if we jump and the index is valid and the sum is also correct, so just apply the sum. Okay. How about the other? All right, this one is also same. We have to make sure that the size is 2 to the power of log, and we start the loop from log -1 in order to avoid out of bound. All right. Okay, so if the sum is correct, so just add. But we should check also if the index is more than n. So sometimes if the index more than n, it is just like all of the value here is 0. So we can jump up to 2 to the power of log -1. But in my implementation, I already make sure that the jump is at most until n, cannot exceed n. All right. Yes. And since we want to find value that greater than or equal to y, I want to find the maximum index first. Maximum index that is still less than x. After that, add by 1. So this is the first index that greater than or equal to x. Okay, yes, just like this, just return current plus 1. And also this, okay, if we want to make sure that the result is not greater than n. Okay, so you already handle it here. Or maybe n plus 1, because some implementation, if all of the value is less than y, so the result is n plus 1. Okay, but all them based on the problem, so we can modify as needed. All right, so is there any question about Fenwick tree? And maybe some of the problem we have ever discussed it. For example, problem A, if we discuss it before, not yet. All right, so let me explain the brief description. So given an array A, and we want to find the number of triplets, triplet ijk, satisfy this. All right. How to find the number of triplets that satisfying this? Okay. So how to solve this? At first, we can do brute force from J. We can use brute force for every possible value of J. Is this from 1 to n or just from 2 to n minus 1? And then we want to find how many valid I and how many valid K. Valid I means the number of I that is satisfying this. And you know, is this value, the value of J and AJ is constant since we did brute force. All right. So how to do that? So at first, let's compress the array since we just need to check whether a value is greater or smaller. So we don't need the exact value. That's why try to compress them. Do you know how to compress a value? Do you know about coordinate compression? Maybe can you implement how to compress a vector of integer, for example? So given a vector v, okay, and then how to compress the value. Yes, we will sort the copy with, okay, Yes, we can compress that. We can use our phone. Yes, it is correct. So the idea is try to sort the copy of the array. So after the array sorted, so we can know which value is same. For example, there are some equal value. So we can remove them using this line. We can use unique queue like this. All right. So now the array is unique, unique queue. So all value in the initial array want to be changed into a value between 0 until n, for example. So just check in this array. For example, there is a value 3. 3 exists in the index 1, so just change it become 1, and then 5 exists in index 2, just change it become 2, and so on. So how to find the index here? Just use lower bound to find the binary search. All right. So after we compress them, the constraint become lower. So AI become at most n, and you know n is at most a million. All right. Okay. And then let let's continue how to find the number of I satisfying this. So at first we will start the array of occurrence. Imagine we have an array of occurrence. So when we iterate j, for example, when j is equal to 1, then a1 is added here. For example, a1 is equal to 7, then 7 occur once. And then after that, when we go to the next iteration, j equal to 2. If a2 is equal to 3, then just increase the occurrence. And for example, 7 come twice, so just increase the occurrence and so on. And then because we already start the occurrence, so when we want to find how many number greater than aj, just try to sum the value here. For example, we want to find the number of value greater than 5. So just sum the occurrence of 6, 7, 8, 9, 10, and so on. How to do that? Just query prefix sum until n, and then excluded by query prefix sum until 5. All right. That's why we already got the sum. All right. You got it? Okay, maybe one of you can implement that part. implement how to find the number of I that satisfying this condition. So it's just like we brute force J and then edit the occurrence, and we will use Fenwick tree here because we want to query prefix sum. That's why we want to update in update point or to point update in Fenwick tree, and then to range query in Fenwick tree as well. Yes, for example, L is the number of I. Okay, really? Okay, let's check the problem. Yes, okay. This is how to find the number of valid I. I think we want to find the value greater than 80. Is it correct? So what shall we do? The number of value for now is j minus 1 and then excluded by aj, I think. The number of value greater. Okay, let's check the problem again. Yes, ai shall be greater than aj. Yes, this is one of the formula because the number of value is j minus 1 for now, and then excluded by all of the value less than or equal to aj. It means we already compute the number of value greater than or equal to j. Sorry, greater than aj. Yes, okay, if we want to reset, actually we can also using one Fenwick tree, but also but without reset. Do you know how to do that? Just iterate it from 1 instead of from n, then update it with minus 1 instead of 1. Okay, you got it? If you don't want to update or you don't want to reset, you can do that. Yes, in order to reset, we can do like this. This is one of the solution. And there is another solution detail which we don't want to reset. All right, but this is also correct. RJ is equal to this, all right, then update AJ. All right, then after we know the number of valid I and the number of valid K, this is the number of valid K. So the number of triplets which j equal to this is Lj times Rj. Right, and I think we need long for some value, so just define integer long. All right. Okay, so you got the solution of the problem. All right. Is there any question about this? Okay, I think the background story also about this. All right. Later we will check who is the author of the problem. All right. Yes, how to do this without resetting the Fenwick tree? Okay, so instead we do this, we can do like this. Just iterating from 1, but we will update it with -1 instead of 1. Okay, so it means we already storing all the occurrence for all value greater than j. Is it correct? Do you agree with this? Okay, just same, right? Okay. So this is the author this problem. Okay, yes. Both of them are correct. So you can try one of them, but maybe this is quite interesting because we don't need to reset. We can reset using this. Just change all of the value become 0. Okay, I think yes. 14 years ago is so legendary, I think. All right, so if there is no other question, so let's continue to problem B. Of course, the problem A, we can also solve it using segment 3. But if you want to solve easier, okay, that's great. Okay. Is he your teacher in the last IOI preparation in 2024? All right, that's great. All right. So, but he never discussed it with you. All right, interesting. So let's continue to problem B. So in problem B, the problem is like this. Given an array and denote a function like this, f, l, r, and x. So this function, the result of this function is equal to the number of in these indexes from L to R that the value is equal to x. All right. Now we want to find the number of pair of I and j satisfying this. All right. Do you have any idea to solve this problem? Okay, this is a senior. All right. Okay, thank you for the information. So how to solve this? At first, there is an observation like this. You know about this formula in the left formula. This value is only based on I and not affecting by j. And for this, it is only affecting with j without affecting I, without affected by I. That's why we can create another function, for example, or not a function, just create another array. For example, pi is equal to f1i ai, and then ci equal to fin ai. So we can reform this formula become pi greater than ci. Is it correct? Okay. Yes. Yes, that's it. Okay. Yes, okay. So we can reform the formula become like this, so it is much simpler. And then what else? Okay. And the other observation is the value of f never exceed n. So the value is quite small. So we can create an occurrence. So just add pi, for example. So p1 is occur once, and then p2 occur once. And for example, p3 is just same as p1, so it is occur twice, and then occur 3 times, and so on. And then just find the number of value greater than ci. So the solution is quite simple, I think. But the difference is in the problem A, we need to compress the value, but for the problem B, we need to find the array P and C. After that, just do like this, just same. Even it is more simple because we can directly add the answer to this. All right. Then how to find array P and C? All right. Okay. There are so many ways. Okay, we can use map in order to find the array B and C. Yes, if we avoid using map, we can use array of frequency, but we need to compress it. I think using map is easier because you don't need to compress it. So actually this is also same map of frequency. So because an array can only storing a million value, for example, and cannot a billion value. That's why we will create a map in order to store just like an array, but can store until a billion. That's why you don't need to coordinate compression. Yes, your idea is correct. Yes, we can just do this, just increase of frequency, because this is means we want to check the frequency of prefix. That's why we will update like this. And then just find the number of frequency of AI. How about see? All right, you can use this idea. So no need to reset the frequency, but just reduce it one by one. All right. Yes, this idea is correct. All right. So after that, just continue using this one, similar with this implementation. Okay. So is there any question about problem B? And of course, you can change the Fenwick tree become segment tree if you want. But the implementation is more complicated. All right. For the map, we can also use dynamic segment tree. But of course, it's more complicated. You can just use map instead of dynamic segment tree. All right. So let's continue to problem C. How about problem C? This is not from code force, right? I think you solve most code force problem. All right. How about this one? Okay. I think headquarter problem is quite short in description. So this just straightforward. So there are n contest round. In each round, for example, in the first round, if our rating is between L and R, then our rating will increase by 1. And then continue to the second round. If in the second round, our rating is between L2 and R2, then our rating will increase by 1 and so on until the last round, which is the end round. Okay. All right. So it will become harder because of there are some queries. So there are queries. For each query given X, which is the initial rating before the first round. And then the question is, what is the rating after n rounds? All right. So can you solve when q is equal to 1? How to solve this problem if q is equal to 1? All right. Is there any idea? Yes, just simulate them. Just iterate for each contest, and then if the current or the current rating is between L and R, then just increase by 1. All right. Then what if there are so many query? How to solve it? Is there any idea? Okay. So how about recomputing all of the answer for all possible x? So for example, we have an array ends. Ends 1 means the answer if the initial rating is 1, and so on until 500,000. All right. So if we know this array, so every time we input x, just output ends x. All right. So this is just O1 complexity. But do you know how to pre-compute all the answer? Do you have any idea? Okay, let's use brute force or naive solution before we optimize it. How to compute this using brute force? Okay, you can solve it in just ON square complexity. Do you have any idea how to do that? Start with 1, solve the segment that affect 1. All right. Okay, we start with 1. For example, the first round covering 1 until 4. And the second round covering 1 only. So 1 is covered by 2. But if we simulate it, from 1 will increase become 2 here, and then not affected by this round. Okay. Yes, we can just simulate all of them one by one. All right. This is also correct. Okay, yes, this is also correct. And how about this? What if we swap the iteration? Can we solve using this iteration? What do you think? Of course, the solution is not like this. Okay, just find the idea if we want to iterate like this. Okay, yes. Initially, the value is 1, 2, 3, 4, 5, and so on. And then for each round, yes, you can increase when this value is correct. Or we can also make the iteration like this. Is it correct? How do you think? Okay, I don't think so. Because the value may be changing. All right. How about this? We can use lower bound. For example, we got L using lower bound and then got R using upper bound. Can we just iterate L and R? Why it is wrong? Can we do binary search? So the condition we can do binary search is okay. Yes. If we want to do binary search, then we have to make sure that the array is sorted. So the question is this array always sorted? How do you think? Always sorted or sometimes not? Yes, always sorted. Yes. Yes, because it is impossible for a value like this and then after the round it is swept. Why? Because if both of them is added, so y is still greater than x. If y is added, so the distance is bigger, so become farther. But if only x is added, so x will be equal to y. And when x is equal to y, then x will always equal to y, never exceed y. Alright, so every time it added, both of them are added. So they are always sorted. That's why we can use lower bound and upper bound. Yes, you need to minus 1 here since it is upper bound. Or if you don't minus 1 here, then just make it less than. Okay, this is also same. Alright, so no need to check again here. Just increase by 1. Alright. Okay, so this is how to pre-compute naively. Alright, now, yes. Okay, yes, now you already got the solution. Yes, that's right. Use Fenwick tree. And yes, we also need to optimize this, right? We we want to optimize this. How to optimize this? Just add them. This just like prefix different idea, right? So in order to increase from this to this, for example, by one, all of them. So the idea is just increasing the left one by one, and then the right, actually right plus one by minus one, and then just do prefix sum. And if we use Fenwick tree, so it means just add this and add this, and every time we want to query, just query prefix. All right, yes, minus one is for R. All right, yes, we can solve it by Fenwick tree. Then, this is a Fenwick tree array. That's why we cannot use our bound directly. Okay, so we need to use that. Actually, upper Ri is equal to what? Can we just use lower instead of upper? Really? Minus one? Okay, yes, plus one. All right. Yes, this is correct. All right, and lower bound is using this. Okay, so now you can solve this problem. Right. I think for this problem, this is quite new problem. This is a contest in 2025. This is a new problem, not a legendary problem. Yes, I think only four days ago, no more than 4 days ago. All right. So, is there any question? Okay. Yes, the solution is like this. So we can output it using get function. Okay. We can also directly do this. Okay, this is just same that you can make it two lines. But do you know, can we swap them? Can we do this first? After that, this? No, yes. We cannot swap this, except we, yes, why we cannot do this first? If we want to swap them, please make sure that this is +2. Do you know why? Because R already added by 1, right? Okay. Yes, that's the problem. Okay, but if you want to use this first, so just +1. And storing in L and R is more safe. All right. All right. So is there any question about this? Yes, I think then we'll go to R. All right. How do you think about this problem? Okay, and then let's continue to the next problem. So in problem G, given an elements like this, given an array, after that there are some query L and R, and we want to find the sum from L to R. All right, but we can reorder the array first before we applying the queries. Sorry, before finding the answer for the queries. And C will want to max the sum of all the queries maximum possible. And we just have to output the sum of the queries. But at first we have to reorder in the optimal way. All right. So do you know how to solve it? Yes, we can use prefix sum. I think without Fenwick tree, we can also do this without Fenwick tree. Okay, yes. All right. Okay, yes. So at first we want to find the contribution value. Yes. For example, if we check for the first sample, when there is a query from 1 to 2, it means 1 and 2 is contributing once. And then if we want to query 2 and 3, then it means this is contributing twice, and then this is once. Because we only want to find the total. So the order is not affecting. Just compute the contribution value. And then we want to find the sum from 1 to 3. That's why add them by 1. So this is the contribution value. Yes, we can find the contribution value using prefix different. Just pref L plus plus and then pref R plus 1 minus minus, and then just do prefix sum. And yes, your idea is correct. After we got the contribution value, just pair the maximum A with the maximum contribution value. So just place 5 here and then just place the others. Okay, so the result is 5 times 3, 15. 3 times 2, 6. 2 times 2, 4. So the answer is 25. All right. Okay. So just sort them after we do prefix sum. So just sort them and then sort the array A and then just find the product, the sum of the product. All right. The sum of the product between two arrays. All right. No need to use Fenwick tree there. And if you want to use Fenwick tree, then just like the previous problem. But since we don't want to find the answer online, so we can use prefix sum instead. All right, let's continue to problem E, and maybe some of you already got accepted. All right, so actually we can use multiset using Fenwick tree. So for problem E, given a multiset consisting of n integers, and then just add k. All right, there are two types of query. The first type is adding or inserting a value, while the second one is removing the kth order. Right. So the array should be sorted. So we can remove the kth element. So how to do that? So we can store the multiset in the form of array of frequency or occurrence, because all of the value is up to n and never exceed a million. Okay. What is the constraint of k? I think k is up to n. Is it correct? There is no constraint for k here. Alright. I hope k is not more than n, since a is also not more than n. Alright. So just create an array of frequency with size n. After that, from the initial array, we can just insert it one by one to the array of frequency. And when we insert an integer, we can also add the frequency. How about remove it? At first, we want to find what is the kth order. After we got the kth order, just reduce it with 1. But how to find the kth order? Do you know how to find that? Yes, just use lower bound in Fenwick tree. That's why we store it in Fenwick tree. Since we need to increase by 1 and reduce by 1, and then we want to do lower bound to find the first prefix that is greater or equal to k. Alright. So for example, the kth element is equal to x. So x is the minimum value that ref x is greater than or equal to k. Okay, because if still less than k, it means not yet. So the first value that is greater than or equal to k means the kth order is equal to x. Alright. So isn't there any other question? Alright, so just use update and binary search. And then after that, just output any value. Okay, this is output any value, so just output the first value if there exists. Just use lower bound again. Alright. And the memory limit is unusual, but if we use Fenwick tree, so the memory complexity is just ON. Alright. That's why we cannot use multiset or polyspace data structure. Alright. So is there any question about this? So let's continue to problem F. If you read this problem and do you understand the problem? Alright, this is graph problem. So there are n distinct items, just like n nodes. Alright. And then for the item, there are some items we must put it before it. So if you want to buy item, it means we have to buy PI1, PI2, PI3, and so on. Alright. And there is no cycle here. So what is the type of the graph? Wait, is there any cycle? What if there is a cycle? Okay, it is guaranteed that there exists a way to pay our items. That's why there is no cycle. If there is a cycle, then it is deadlock. We cannot buy any of them. Yes, but yes, that's it. So that's why the author guaranteed that. Yes, so the graph is directed acyclic graph. We can conclude it from this and from this as well. All right. Now, do you know we will buy them in n days. So one day, one item. And we want to make it lexicography smalls. Yes, that's it. We just like want to find the lexicographically minimum topologically sorting of it. Yes. All right. And what makes the problem harder? Do you know what? Actually, it is just toposort to find the lexicographical smallest. But what makes this problem harder? So here, for each item, there is an index and a serial number. They are different. All right. Okay. Item means this is index. How about lexicographical smallest? We want to minimize the index or serial number. How do you think? Yes, serial number. Just just like this here. Serial number. So they are different. Actually, the initial serial number is I minus 1. Alright. So from 0, 1, 2, 3, 4, and so on. But unfortunately, the serial number is changing for each day. Alright. If today the serial number is X, then tomorrow the serial number is changing become X plus D modulo N. Alright, let's make the problem harder. Alright, so how do you think? What does it means? So for example, in the first sample, the graph is like this. Wait, I think the index is okay. Yes, let's make it one piece at first. All right. This is the index, and the serial number initially 0, 1, 2, 3. So the only item we can buy is this. Okay, yes. Alright, yes. That's why the first value is 1. After that, since t is equal to 1, so the serial number is changing. Become 1, become 3, and then this become 4. That's why we can take either this or this. Sorry, this is not 4, but become 0. Okay, so we can take either 1 or 0. Which one we take? Of course, we take 0 since we want to find the SU graph is smaller. After that, again, the value is changing. This become 2, and then this become 0. Again, we can take 0. After that, it become 3, and then the only item left is 3. Okay. Yes, you already got the idea. What is it? Yes, just like finding the minimum topological sort. But we want to find the minimum serial number. How to do that? Yes. Yes, you can do that. That is one of the solution. There are some other solution. Okay, so okay, if you use that solution or that idea, we just like creating a what type of data structure? How do you think? Using which data structure in order to solve that? Which data structure can give the minimum and can add? Okay. Yes, there is a solution using Fenwick tree, but can we use that? Can we use Fenwick tree for that idea? So we need to find the minimum, right? Minimum of all of them. How to do that? And sometimes we want to add t. We need to shift the count. How to shift the count in Fenwick tree? Can we shift the array in Fenwick tree? I think Fenwick tree doesn't have an operation, doesn't have shifting operation, right? How to shift the, is there any idea how to shift? Okay, yes, shifting idea is correct. So actually it is just like we are shifting from 0 become d. So the last d become the smallest value and then continuing with the rest. Okay, just like cyclic shift. Alright, but which data structure can accommodate this? The Q, but what is the value of G? Okay, G is up to 100,000. So we move it 100,000 or at most 100,000 divided by 2. And we will do this n days. So too much value need to move. How do you think? Can we use segment 3? Okay. If you want to use segment 3, so you have to know which value need to add with D and which value need to add with D minus N, right? Do you know what I mean? So for example, now the value is like this. So okay, we can also use pointer. So if D is equal to 3 means we will add them by 3 and reduce them by 6. Is it correct? Not 6, I think reduce by 7. Alright, we can do that. And we can do minimum segment 3. We can create a minimum segment 3 and the update operation is increasing or decreasing the segment. So we need to do lazy propagation. We need to create a lazy seg tree. And we also need to store what? How to do topological sort. What should we store in order to find the topological sort? Yes, the number of kernel in degree. So, for example, the first in degree here is 0, and then this is just 1, this is just 1, this is 2. And we only can take the value that the in degree is 0. That's why it is quite complex, since in the segment tree we need to store serial index and also the serial index and also the in degree and also serial number. So when we want to find the minimum, we got 0 and the serial number. Alright. So we just want to find the minimum among all pair like this. And the number sorry. There are two types of update if we use segment tree like this. The first type is adding or decreasing a segment, and we use lazy propagation there. Then we also need to create another operation, which is reducing the integrity, right? Okay, so it is quite complex if we use segment tree. So can we solve it easier or simpler? Just use Fenwick tree. How do you think? Fenwick tree will storing what? We will have Fenwick tree and also array of integrity. This is just array, and then this is a Fenwick tree array. What do you think? Do you have any idea to solve this? So just like if we want to find the topological sort, we need to start integrity, right? So every time we take an item, so just reduce the integrity. What if the integrity reach 0? What shall we do? For example, initially the integrity is 1 and then reduce it by, yes, just add, not add the serial, just add this by 1. And this is still storing index, not serial, just an original index. So it is easier to implement. So if the index of this node is 4, just increase index 4 in the Fenwick tree. And if the other value is become 0, and then just increase by 1. Or in the initial, if there are some nodes that the degree is initially 0, so just make it 1. All right. So do you know how to find the minimum serial number among all 0 in degree? How to find it? Do you know how to find it? Actually, this is still in the form of index, and the index is already changing, plus d times j modulo n. It means the 0 index is the index where the value is equal to this, right? So at any value, this is actually the serial number is 0, 1, 2, 3, 4, and so on. So just use lower bound, right? Find the first value that is started from this. If there is no value here, so just find starting from this. All right. Finally, we can solve it easier and simpler. And the complexity is still n log n, not n log square. All right. Is there any question about this? Okay. So good luck to solve the problems. And only problem F left. all of the other already solved by at least one of you. Congratulations. And so see you again in the next meeting, inshallah. And that's all for today. Let's close our discussion with praying kafaratul majlis. Subhanakallahumma wa bihamdika asyhadu an la ilaha illa anta astaghfiruka wa atubu ilaik. Wassallallahu ala nabiyyina Muhammadin walhamdulillahirabbil alamin. Wassalamualaikum warahmatullahi wabarakatuh.